Our goal here is to align these three joints so that when this is rotated, it gives rotation in a plane that is equivalent to that of a triangle. So I was going to show this earlier. What we have here is a triangle between any 3 points in space, provides you with a triangle. So if you have any 3 points in space, and let's get rid of the rest of the skeleton here just to kind of minimize and make an explanation here. We have three points in space right here, create a triangle. Let's even simplify it more. Let's turn off joints. So if you start to see the arm as a series of vectors and a triangle, once you think of it this way, and you start to think of it this way, you can start to see the potential for using linear algebra and use it to solve a lot of your different alignment problems. So you can get the vector from the shoulder to the elbow, the vector to the wrist, or a series of vectors emanating from said elbow down to the wrist and the shoulder, or from the wrist going to the other joints. You can even add and subtract these vectors. The possibilities become limitless on how to use this information in PyMEL and arranging vectors and matrices, which I'm about to show you here. I just wanted to show you that you have to start thinking of things this way. Any 3 points could be this. This could be a finger. This could be your spine that's aligned in, say, the X or the Y or the Z axis already for you. And you can use those presuppositions to align spine joints or whatever. So we're going to make a script that's very generic and will align any 3 joints. Okay. If you'll recall earlier, we had a vector of 3, 4, 5, and I'm using this little red poly tube thing to represent this vector now. So we had a vector that pointed off in space at 3, 4, 5, and you'll recall its length was 7.071068. Sometimes in matrix math and linear algebra, you need what's called a normalized vector, a vector that points in the same direction but is only the length of 1. And I'm going to show you how to get that right now. So let's go to the script editor. Okay. Clear the history and import PyMEL as always. Okay, so first let's create a vector that represents our existing long vector. So we'll say vec is equal to pm.dt.vector. And we'll go ahead and make it a tuple, 3.43, 4, 5, and close that off. Okay, so let's go ahead and check the length of that, vec.length, just so we're sure. Okay, so it is the exact same as our measuring device out here. So you can see this is just truncated a little bit, probably for sanity and visual capability. So there is a normal method. So if we did C on vec, because I love to do the C, you could see that there are 2 methods right here, normal and normalize, and I'll talk about each one right here, right now. So let's go ahead and do that. Let's see if we can get normalize to give us a value. So if we say, let's go ahead and comment this out, we'll say normalized vector, okay, and we'll call it vec norm is equal to vec.normal. Okay, we'll run this. And let's look at vec. Let's just see what vec norm. Let's just see what the values are. They're all less than 1. They're pretty small. And they're all decimal values, long decimal values. And vec norm.length is in fact 1.0. Well, it's pretty close. It's very close. So that's close enough for what we need right now. Let's go ahead and put a locator at that position right now, just so we can visually see where it is. So let's create a little locator. So loc is equal to pm.space locator. Just create, I don't care what it's named right now. Oops, Control Z. Okay, that created a locator. You can see that guy, he's at the origin right now. And we'll just say loc.translate.set. And we're just going to set you to the value up here that's vec norm. Control copy, Control V. Sometimes I forget I'm not in Linux. Okay, let's move this up here so you can see. Alright, so I just told the locator to translate in space to the position that is the value of vec norm, and we remember that value here. Okay, so let's go ahead and advance the timeline forward 1 frame so you can see what I got here. So here is a new little vector. It's much shorter, about 1/7 the length of the original one, but it does point in the exact same direction. And let's just verify that the length is 1. So the length is 1 here. Well, it's close enough. And I did put a little measuring device, a little measure tool from Maya on that. So let's move forward and just see what that looks like. And it is this one right here. So it does, in fact, it is point constrained to this locator right here. So it does, in fact, measure out to be 1.0 for all intents and purposes. So to reiterate, a normalized vector is a vector whose length is 1, not 7 point whatever, right? And you definitely need a normalized vector for some of the calculations that we're going to perform here. So when I refer to a normalized vector later, I don't have to explain it. You know that it's going to be a vector that's very short, and all the values are probably 1 or less, and the value of the length of the hypotenuse, or the magnitude, is 1.0. And to add, because I had brought it up earlier, what normalize is. So let's go ahead and evaluate vec again. So if you highlight vec and get the value, it's 345, originally what we had set it to, right? But if I wanted to get the normalized version of that in place, vec.normalize is the command that we would do. And when I say in place, it doesn't spit anything back. So I could run it a few times and nothing would happen. But if I went back to this vec and instead evaluated it, it gives me back a normalized version. So I actually modified my original vector. Sometimes that's not what you want. You want to be able to know the distance and the position of something, so you kind of probably don't want to do that. So I would suggest using vec.normal and get a normal vec. And this also will allow you to troubleshoot if things aren't working properly using the logging debugger.